Alrighty, let's pick up part 2 of this partial fraction decomposition. This time, let's
Sorry,
actually
I'm
try
not
to.
sure about that.
I don't know what Alexa is going crazy for. Sorry, Alexa, I didn't talk to you. So let's actually work on some problems. So let's take it all the way through. Okay. Find the partial fractions of something like this. From the discussion in the previous PowerPoint, do we know exactly what to write as partial fractions? Like write this as we say, because these are linear non-repeating factors in the denominator and it's a proper fraction, we'll say a over x minus 3 plus b over x plus 2. Right? There are about 2-3 methods to solve this case 1 problems. So let me discuss 2 of them right here. Method 1, this is a method that works for all the problems. So what do we do? To begin with, we will write down this stuff like a over x minus 3 plus b over x plus 2 and things like that. And in the next step, let's multiply both sides by this big denominator, x minus 3 times x plus 2. Cool? What would you get on the left-hand side if you multiply by this denominator? Well, the denominators divide into 1 and reduce to 1, and you get 5x minus 5, right? Cool. So 5x minus 5 on the left-hand side. What about the right-hand side? So notice we are talking about this denominator times a over x minus 3. So x minus 3 and x minus 3, they reduce to 1, and we end up with a times x plus 2. Similarly, plus b times x minus 3. We're good? So now, here is where the different methods differ. At this stage, we can just multiply out, distribute the whole thing out, and gather all the like terms. What do I mean by that? The terms that have an x in them and the constants. So gather the terms with an x in them. So you get x times a plus b, and the constant is 2a minus 3b. Simple? And now here is the idea. We have 5x minus 5 equals x times a plus b plus 2a minus 3b. Of course, there's all this stuff in between, but because we have equal signs, the way it works is a equals b equals c equals d means a equals d. You agree with that? A equals b equals c equals d. That means a must be equal to d according to mathematics. So we can say 5x minus 5 is equal to x times a plus b plus 2a minus 3b. Now this is not just an equation. It is more than an equation. It is actually an identity. What does that mean? It is an equation that is true for all values of x. I can plug in any number for x and this must be true. I must pick a and b in such a way that if I plug in any number for x, the left-hand side must equal the right-hand side. Now, the only way that can happen is if the like coefficients are equal. Watch that phrasing. The only way these two things would be equal, and this is an identity, is if the like coefficients are equal. What do I mean by that? What I mean by that is the coefficient of x on the right hand side must be equal to the coefficient of x on the left hand side. What is the coefficient of x on the right hand side? Meaning that's a fancy way of saying what is x being multiplied by on the right hand side? A plus b. Cool. What is x being multiplied by on the left hand side? 5. Cool. So a plus b must equal 5. That's all I'm trying to say. And also, is there a constant on the right hand side? Yep, this 2a minus 3b. And is there a constant on the left hand side? What is the constant on the left hand side? I hope you didn't say 5. The constant is actually negative 5. right? So be careful. So the constant on the left hand side is -5. So equating the live coefficients, we have a plus b equals 5 and 2a minus 3b equals -5. And what are we trying to do? We're trying to solve for a and b. How many unknowns is that? 2, a and b. How many equations do we have? 2. Are they linearly independent? What? Yeah, don't worry about it. So if you understood it, that's fine. If you didn't understand, don't worry about it. So can we solve these two equations? Yep, we can. There are many ways, and one way I like is, I noticed that there's a 2a minus 3b. There's a 2a here, and there's just a single a. So I want to get rid of a by multiplying the first equation by 2. The whole first equation, both sides, multiply by 2. You get 2a plus 2b equals 10. So that's what I wrote here. And 2a minus 3b equals -5. Write that underneath this. And if you now subtract the bottom equation from the top, the a's will cancel. The 2a and the -2a will add up to 0. And you have 2b minus -3b, or 2b plus 3b is 5b, and 10 minus -5 is 15. So you end up getting 5b equals 15, b equals 3. Right? And now we can use this first equation, a plus b equals 5, and plug b equals 3, and that gives us a equals 2. Immediately we can conclude a must be 2. So that's how we figure out a and b. What's the purpose of figuring out a and b? Now we did split this partial fraction into two. We split this polynomial. Wake up, Sammy. We split this rational function into two partial fractions, right? With a being equal to 2 and b being equal to 3. And so we have this. Cool? All right. So I'll solve quite a few problems. So if you need to, go ahead and rewind and watch this over again. But this is a simple, straightforward process. Next, same problem, but method 2. Now it works for all problems, but best suited for case 1. Okay, and so here is the idea. We pick this up and say that's a over x minus 3 plus b, and multiply both sides by this big denominator, and that gives us this equation. And I said this is an identity, so that means it must be true for all values of x. Exploiting that, we will do this. We can plug in whatever value we want for x. And now I'm going to be a bit clever about this one. And I'll say, let me plug in x equals -2. Right? Do you see why that's a clever thing to do? If not, it'll become obvious in just a second. So go to this equation, identity, and plug in x equals -2. So the left-hand side becomes 5 times -2 minus 5 is -10 minus 5, -15. The right-hand side becomes a times -2 plus 2. Hey, wait a minute. -2 plus 2, isn't that equal to 0, man? Yep, it is. A times 0, hey, that's 0, so a is gone. Dang, Dr. Sam, you are really clever, man. No, don't praise me. I shamelessly copied from somebody else. Okay, so a term is gone, and we have b times -2 minus 3 is -5. So we end up getting -15 equals -5b, which means b must be equal to 3. Done. Right? And next, let's plug in another value. Now it's your turn to be clever. We already got the value of b, so we'll get rid of b. Did you get it? Dang, you guys are good. So you did say put x equals 3, right? Yep. So plug x equals 3 into that same equation, and you get 5 times 3 minus 5 equals this. And sure enough, the b term disappears, And you get 15 minus 5 is 10. 10 equals 5a, and a equals 2. Ta-da! So this is the second method. There's a third method for case 1, which I'm not going to discuss right now, and I'll do it in next PowerPoint. It's a quick and dirty way. That's a real clever way. Okay, so the final answer is this. Cool. All right, let's pick this one. When you look at it, can you tell me what partial fractions you should write? Did you say a over x minus 3 plus b over the quantity x minus 3 square plus c over x plus 2? If you did, pat yourself on the back. Now what do? Multiply by the big denominator both sides. When you do, the top becomes, the left-hand side becomes just the top, and the right-hand side, x minus 3's, one of them cancel out, and you end up with this. I hope I don't need to discuss this algebra in detail, right? And you get that. All right, now what do? Well, according to this method 1, you just need to multiply everything out, FOIL everything out, and collect all the like terms. And there's a systematic way in which you can do this. Okay. Oh, and by the way, get used to doing stuff like this. You have a whole bunch of terms, and now you need to collect the like terms thing. Oh boy. In mechanical engineering, I told you that my PhD is in mechanical engineering, right? Oh, bachelor's, master's, and PhD, all of them. I took a class called Dynamics of Machinery. There was a situation where you had to balance a mechanism, a 6-bar mechanism. In that one, boy, we ended up with about 50 or 60 terms in just one equation. And then you had to pick up all the like terms and put them together. So the amount of patience required in that one was tremendous. So if you're looking at this one and going, oh my gosh, man, there are so many terms in this, you ain't seen nothing yet. Okay, so what's the systematic way? I would first say x square. Immediately I'll just say x square. And then I notice that means that we would have an ax square from this product. Anything else with an x square? Nope. Hey, there's a cx square. So x square times a plus c. Done. The x square is done. Plus x times, wait, there's a minus ax. Oh, so negative a. There's a plus bx. Oh, plus b. Minus 6cx. Oh, so minus 6c. So x times all of those things. Finally, plus a constant. There's a times negative 6 is negative 6a, 2b, and plus 9c. See? That's how you do it. And now we apply the concept called equating the like coefficients. Coefficient of x square on the left hand side is equal to the coefficient of x square on the right hand side, which gives us a plus c equals 5, right? X square is being multiplied by a plus c. X square is being multiplied by 5 on the left hand side. So that's why a plus c must equal 5. Similarly, x is being multiplied by negative a plus b minus 6c on the right hand side, and that must equal negative 14, which is on the left hand side, and so on. Constant equals constant. So now we have 3 unknowns, a, b, and c, and there are 3 linearly independent equations, and we just solve them. Simultaneous equations in 3 unknowns. I'm gonna, did I? Oh, I'm such a nice guy. I'll show this to you. I'm not gonna discuss this with you. You figure out. Okay, so it's a matter of solving equations. And you get a equals 3, b equals 1, c equals 2. And so that means we're done. Cool. So be sure to write the final answer. It's always a good idea to write the final thing. Okay, now let's go to method 2. Method 2 works, but not as well as it does for case 1. We can still, what was method 2? Hey, be clever and plug some numbers for x, it said. Right? Cool. Can you think of some number for x that you can plug in which will make your life simple? Notice there's an x plus 2 that's being multiplied, right? So what about picking x equals -2? Is that a good idea? Yeah, that will cause this first term to go to 0, -2 for x. A will also luckily make the second term go to 0, the b term. And only thing that would be left with is c. So we can solve for c. What else can we do? I'll come back again the second time and plug x equals 3. That gets rid of the first term and the third term, so allows us to figure out b, right? Let's see. Okay, I got into a new slide. All right, put x equals 3, just like I said, and when you plug, you get 5b equals 5 and b equals 1. Now put x equals -2. Like I said, the first a and b terms go to 0, and we end up with 25c equals 50, so c must be 2. Now, see, there's a little issue here. What are we going to do? What do we plug now? Well, the thing is, we can plug any number for x. So why don't we plug x equals 0? Would it cancel out all the other terms and just leaving us with 1? Especially, would it just leave us with a? No, it won't right away. But it's not a bad idea. So let's put x equal to 0. And when we do, we end up with b times 0 plus 2 plus c times all of this. Our objective is to find a. Any idea how to do that? Hey, wait. Did we already know the values of b and c? Yeah, why don't we plug those in? So, while it is not totally straightforward like how it was in case 1 situation, this is not so bad. In the next step, we'll plug in 1 for b and 2 for c. And that gives us a equals 3. Cool? That is the idea. So put x equal to 0 and solve for a. And so we got a, b, c values, and we split this into partial fractions. Let's see. All right, any ideas? Yeah, the ax plus b over x squared plus 4 stuff, plus c over x minus 1. Again, multiply both sides by the big denominator. We end up with this. Multiply out everything, gather up all the terms, and assemble like that. Set like coefficients equal, and you get 3 equations like this. Setting coefficient of x squared equal, you get a plus c equals 6, and x you get -a plus b equals 1, and so on. 3 equations, 3 unknowns. Solve. And you get a equals 2, b equals 3, c equals 4. And interpret that by plugging back into the original thing that we started with, and we are done. You get the hang of this? You just practice a little and you should be fine. As long as you are careful in your algebra and arithmetic, this should be fairly straightforward. Okay. Alrighty, let me continue with another one. I'll start with not you, man. The other guy, where is he? 3. Yeah. So I'm picking up the problem that we had in the previous slide, the very first problem that we attempted. And I'm trying to show you a method 3, and it works only for case 1 problems. Okay, you must have non-repeating linear factors. It doesn't matter how many non-repeating linear factors you have in the denominator, but it works only for that case. Okay, please pay attention and learn this method. I don't know why some students get it right away and they're like, hey man, this is the best thing that I've ever seen. And some people, for the life of them, they don't understand this at all, and I can't understand why they don't get it. So, without much further ado, here is the idea. What do we do typically? We say a over x minus 3 plus b over x plus 2, right? Don't say that. Just say blank. Leave that as a blank over x minus 3 plus blank over x plus 2. Simple enough? Okay. The idea is we are going to figure out what we should get on each of these tops. And to find what goes here on top of x minus 3, set the x minus 3 equal to 0 and solve for x. Simple enough. Set that x minus 3 equal to 0, the denominator, and solve for x. What do you get? X equals 3. Right? Now, take that x equal to 3, take that value of x equals 3, and plug onto the left-hand side. Cool? Take that x equals 3 and plug onto the left-hand side. But wait a minute. Can you? What's going to happen to the denominator? That denominator is going to go to 0 because 3 minus 3 would become 0. Right? And because that 3 minus 3 will go to 0, just cover it up. Be sure to cover up that factor that equals 0. In this case, that 3 minus 3 is 0. X minus 3 will become 0, so cover it up. And into the rest of it, plug x equals 3. So that means we would have 5 times 3 minus 5. You don't need to be macho, go to the side. 5 times 3 minus 5 over 3 plus 2, which is nothing but 10 over 5 is 2. Ta-da, that's 2. Isn't that simple? I know when I explained it to you, it took a few steps and it took some time, but the process is very, very, very simple. Right? Let me go backwards. And okay, what was the idea? To find what goes here, what's the first step? Set x minus 3 equal to 0 and solve for x. You get x equals 3. What do you do with that x equals 3? Plug that onto the left hand side. But because this x minus 3 will go to 0, be sure to cover that up. And only into the remaining stuff plug that x equals 3. 5 times 3 minus 5 over 3 plus 2. I figured that out on this side. That's equal to 2, and that's what goes there. Cool? Oh, I didn't do that, did I? Oh, man. Okay, you tell me. What should we do? How do you figure out what goes on top of x plus 2? Set x plus 2 equal to 0, solve for x, you get x equals negative 2. Plug negative 2 on the left hand side, but notice this one goes to 0, so cover up the x plus 2, so we have 5 times negative 2 minus 5 over negative 2 minus 3. That's negative 15 over negative 5 is equal to 3. So this becomes 3. As simple as that. So that's something that I wanted to show you, and please learn this method. It'll come in useful very, very, it comes very useful. English, Sammy. It comes in very handy in differential equations and in all kinds of courses that you take. Okay, so please be sure to do that. Now, one last slide. One last PowerPoint. Yeah. Let me wrap up the whole thing. Now here is a situation where we have an improper fraction. If that means the degree of the top is either equal or greater than the degree of the bottom. So in a case like that, let me illustrate with some simple cases, and actually I'll go ahead and do some integral problems. Oh, by the way, I didn't tell you this. Why are we learning all this stupid partial fraction decomposition? I thought we were studying integrals, man, right? Oh, darn. I didn't address any of those questions. The whole idea was whatever we split into partial fractions, imagine if they were to be integrals. So the idea is to integrate them the way they are. Those rational functions would be difficult. But the moment you split them into partial fractions, each integral becomes an easy one to integrate. That's the whole idea, right? That's why we are learning partial fraction. Oh, I'm so stupid. I didn't even mention that. Sorry about that, guys. All right, so let's look at this one. How do we do this? Do we have a polynomial over polynomial? Yeah, first degree over first degree. So that's not quite a... is it a proper fraction or not? For this case, we'll call it, no, it's not. We'll say the numerator has to be strictly less than the denominator. Since this is not the case, how do we deal with this? One way is, could we be clever about this? We notice that the denominator has an x plus 1 and the numerator has just an x. So let's go ahead and write the top also as x plus 1 first. But okay, oh yeah, but compensate for adding that 1 by subtracting a 1. Now would you agree that the top reduces to just x? So we can call this as equal to this. That's the idea. Why, man? Why did you do that? Well, when we do that, now we can split this into two fractions. We can say x plus 1 over x plus 1 minus 1 over x plus 1. Right? We can split the a plus b, the quantity over c is a over c plus b over c. What is that? A plus b all over c is a over c plus b over c. That's okay. So this gives us a nice thing like this. Now, how do we integrate this? Integrate 1, you get x. Integrate 1 over x plus 1, you get natural log of absolute value of x plus 1. And so x minus natural log of absolute value of x plus 1 plus c. Done. Right? That's the idea. 2. Yeah, what do we do in this case, man? 4x, bottom we have a 2x plus 5. We want to get a 2x plus 5 on the top. Well, how about this? Can I write the top as 2 times 2x? What was the idea? My eventual objective is to get a 2x plus 5 on the top. But right now, at least I have succeeded in getting a 2x by factoring out a 2 and getting 2 times 2x. So what I'll simply do is I'll add a 5, 2x plus 5, and subtract a 5 to get rid of whatever I added, because I cannot just add whatever I want. I'll just compensate for it by subtracting a 5. That's what I do. That makes sense? So this is back to being 2 times 2x, right? When you simplify. Don't simplify. That was not the idea. And so now we can pull this constant multiple 2 outside if you want, and then write this and look at this as the quantity 2x plus 5 minus the quantity 5 on the top over 2x plus 5. We already pulled that 2 outside of the integral, constant multiple. And so Now, does it look like a plus b over c, which is a over c plus b over c, or a minus b over c? A over c minus b over c? Yep, that's what we do. And so 2x plus 5 over 2x plus 5 is 1, minus 5 over 2x plus 5. Can we integrate 1? Yep, that's equal to x. Can we integrate 5 over 2x plus 5? I don't know, man. Well, that's just going to be minus 5 halves. There's already a 2 outside. 2 times 5 halves natural log of absolute value of 2x plus 5. Remember that 1 over ax plus b, we did an integral of 1 over ax plus b. That's the form of this one. So we end up with this. Cool. Yeah, I just distributed the 2. That's a final answer. Okay, what about this one? I see. Somehow we need to get a 4x plus 3 on the top, and right, that was the idea. Well, can I do that as a first step? Factor out a 3 so that the coefficient of x becomes 1 inside the parenthesis. Now can I can I multiply just the inside stuff by a 4? Right? I multiplied both the terms by a 4. So 4x minus 8/3. But because I multiplied by a 4, I'm dividing by a 4. These are all clever ways. I don't know if it's necessarily this is a good technique here. We could actually do a long division. That may be a better one for this problem. But I just wanted to stay with that clever method. And so 4x minus 8/3. But we want a 4x plus 3. No big deal. We'll add a plus 3 and subtract a 3 from the top. That's what we do. And then this simplifies to 4x plus 3 over 4x plus 3. And negative 3 minus 8/3 is negative 17/3. You just sort of cross multiply. Negative 3 times 3 is 9. Negative 9 minus 8 is negative 17 over 3. And so we got 3/4 on the outside, and we split like this, and that's the integral. So these are the cases where we have a linear polynomial over a linear polynomial. Okay. What next? Now let's consider higher degree rational functions. Now clearly the degree on the top is bigger than the degree on the bottom, 3 versus 2. And so what do we do now? Here, greater than degree, so we perform a long division and rewrite the expression. We perform a long division. Y'all remember how to do long division? Well, I'm going to show you back again. So you write the denominator becomes the divisor. Those are the words, right? The denominator is the divisor and the numerator is the dividend. But make sure that if there is some term missing, like x squared term is missing, be sure to say 0x squared, and also arrange these terms in descending orders of powers of x. You must do that, and wherever you have a missing term, you must put a 0 and that term. Cool? Okay, and now what is the first term of the quotient? Here is the idea. Pay attention, please. Pick the highest term in the dividend, which is 3x cubed. Now pick the highest term in the divisor, which is x squared. And figure out what 3x cubed over x squared is. Highest term in the dividend over highest term in the divisor. Can you do it in your head? If not, go to the side and figure it out. So 3x cubed over x squared is 3x. See, I do have it on the side, which is equal to 3x. Take that 3x, and that was what's the first term of the quotient. Now, multiply that term that you just added, multiply that term by the divisor, and write the product underneath the dividend. So 3x cubed minus 3x squared minus 6x, like that. Cool? And subtract the bottom from the top. So 3x cubed minus 3x cubed goes to 0. 0x squared minus negative 3x squared becomes positive 3x squared. 4x minus negative 6x is 4x plus 6x, which is 10x. So that just becomes 3x squared plus 10x. Cool? Now bring the next term in the dividend down, that minus 2. Cool? Now, carry out the long division once again. Try to figure out what the next term in the quotient would be. For that, again, pick the highest term here, which is 3x squared, divided by that the highest term here, which is x squared. 3x squared over x squared happens to be 3. So plus 3 is what you do. And just take that 3 and multiply by this one, the divisor. And so you get 3x squared minus 3x minus 6, right? Excuse me. And subtract the bottom stuff. That goes to 3x squared minus 3x squared is 0. 10x minus negative 3x is positive 13x. Negative 2 minus negative 6 is negative 2 plus 6, which is 4. So you end up at 13x plus 4. How long should we keep going? Check this out. So this is the remainder now. What's the degree of the remainder? 1. What's the degree of the divisor? 2. If you get to a stage where the degree of the remainder is less than the degree of the divisor, that's where you stop. So the remainder is 13x plus 4 and the quotient is 3x plus 3. Okay, since the degree of the remainder is less than the degree of the divisor, we stop. And that is the quotient, and this is the remainder. And how do we interpret all this stuff? Here is the idea. We say that is equal to the quotient plus remainder over the divisor. Cool? Quotient plus remainder over the divisor. Do I show that? Yeah. And now, the whole idea was, how do we integrate this one? Right? So, if we look at this original one, imagine this being an integral problem. Integral, hey boys and girls, what's integral of 3x cubed plus 4x minus 2 over x squared minus x minus 2 dx? Whoa. Well, the moment you split this into partial fractions like this, well, at least right now, we did the long division and we got these. Can you integrate 3x? Yeah, piece of cake. 3, piece of cake. We got this. How do we integrate this? Well, for that we need to split into partial fractions. Let's embark on that. Denominator can actually be factored. We can write that as x minus 2 times x plus 1. Let's do that. And now, can we use that method 3? Linear factors. Blank over x minus 2 plus blank over x plus 1. If you do that, trust me, try it, you end up getting 10 over x minus 2. Can I quickly show that? How come this is 10? That's because set x minus 2 equal to 0, x equals 2, cover up x minus 2, so plug 2. 26 plus 4 is 30, 30 over 2 plus 1, 30 over 3 is 10. Ta-da! X plus 1, set it equal to 0, x equals -1. Cover up x plus 1, plug -1 on the left hand side. So this is -13 plus 4 is -9 over -1 minus -2, and -1 minus 2 is -3. -9 over did I goof? -1. So that's -13 plus 4 is -9 over -3. Ladies and gentlemen, I goofed. This is supposed to be +3. Oh, wow, glad I checked that one. So that should be a +3 there. But hopefully, so let's make this into a plus. And we integrate every one of those terms. Okay, that's the idea. So you got to learn how to do long division. Now I'm saying let's revisit the 3x minus 2. This was the one that I said perhaps it's not a good idea to try to be clever about this one, right? So let's do a long division on this one. Probably is easier. What's the first term of the quotient? What did I say we needed to do? The highest term in the dividend over the highest term in the divisor. So 3x over 4x. What is 3x over 4x? Is 3/4. Guess what? That's your first term of the quotient. Now what do? Take that quotient and multiply, take that term in the quotient and multiply 4x plus 3. And you get 3x plus 9/4. Subtract. You get 3x minus 3x is 0. -2 minus 9/4 is -17/4. Should we stop? Yes, because this is a constant whose degree is less than the degree of this one. So constant is a 0th degree polynomial, whereas the divisor is a 1st degree polynomial. We stop and we interpret this as the quotient. That's the quotient, and this is the remainder. Whoops, I didn't even bother to do this. Oh, I did right here. Okay, there it shows up. The quotient plus the remainder over the divisor. And because the remainder happens to be -74, I said -17/4 over 4x plus 3. Right? Perhaps for this one it's not a good idea to be clever, and we are better off using this one. Either method is fine by me. Cool? Folks, I think I have taught everything that you need to know in partial fraction decomposition and solving integrals. And good luck.